In this video, we're going to discuss graphs of algebraic functions. Learning objectives are understand how graphs work in terms of input and output quantities. Then understand and identify types of transformation of functions. And be familiar with basic functions. Those are also known as toolkit functions. And understand piecewise functions. So in this section, we're going to investigate several different types of function with their unique attributes. Okay, so attributes as in specifically in terms of graphs. Therefore, it is essential that you understand the definition of functions, as we learned in Module 1. Because the graphs we're going to look at today will reflect the definition of function, since we're looking at function graphs. So be able to identify a function given a graph or table and come up with a function fitting different classification, as we did in previous example as in Module 1 and Module 2. Because sine, cosine, tangent are also functions in trig Module 2. This video will show graphs of toolkit functions that we need to be familiar with in terms of shape and notation. So make sure if you're not comfortable with definition of function, review Module 1. And a graph represents relation between input quantity and output quantities as defined by definition of function. So first, we're going to look at an example just for us to get engaged. So I would like you to actually get a piece of paper and try this together. Okay, so we can really think about the graphs in terms of function. Okay, so consider the time that it would take to pick all apples at one particular orchard as a function of the number of workers picking up the apples. So I'd like you to sketch, again, there's no necessarily one correct answer. I'd like you to sketch a graph, the time it takes to harvest the cropped apples as a function of number of people picking the apples, and label your axes. Okay, so I'd like you to pause the video and just sketch whatever you think is a valid model for this scenario. So here, there are many different possibilities. You should look for some commonalities between possible solutions. Many possible solutions are both decreasing and concave up. Okay, so concave up, we'll talk about that in a little bit. Whichever graph you draw, make sure that you can justify the features of it, because we can have many different scenarios, how many workers we have, right? There's many different aspects of graph that could look different from yours to mine. Okay, so this is just more of a warm-up exercise. Okay. So, next question. The graph you draw, is that a straight line? Why or why not? Again, there is no necessarily a correct answer here. We're just trying to have you think about the graph and the function in terms of input and output quantities. So input quantity could be time, or output quantity could be number of workers, or vice versa, whichever you chose to be input quantity in this scenario. Okay. So try to answer this question. So there are many ways to see it should not be a straight line. So here's one compelling reason. Again, there's no one answer fits all here, because the scenario can be different from person to person's graph. So suppose T is the amount of time it takes a single worker to harvest the field. The time it takes 2 workers to harvest the field ought to be half of that, so half of T. That is increasing 1 worker to 2 workers, so increase of 1 worker, causes the amount of time it takes to harvest the crop to be reduced by half. So that's why we do half times T. But increasing from 2 workers to 3 workers cannot possibly cause the same decrease in the harvest time. As you can see, the ratio is different, right? As they will be saying that 3 workers can harvest the field in no time at all. Okay. So again, here, we're just trying to get ourselves thinking in terms of what does graph represent in terms of 2 quantities. Okay. So the next question, Again, if you need to, please pause the video and think about this. Is the graph you drew continuous or discontinuous? As in, was the graph just like a curve, or even if it was a straight line, were there any discontinuity, or is it just a line? So here, both models are reasonable. Okay. So on the one hand, you might say that you can never have, say, 1/3 of a worker. So number of workers must be a positive integer, such as 1, 2, 3, 4, 5, and so forth, right? That means that the domain of this function ought to be a positive integer. So this is when we think workers as input quantity. So there is no way the graph can be continuous. Right? So if we were to graph this, we have some dots at 1 worker, 2 worker, 3rd worker, and so forth. Okay. On the other hand, we'll very often model decisions like this using a continuous model just for prediction's sake. Okay. And this will allow us to use tool calculus, which we will learn in calculus class, since this class is to prepare for calculus class. But again, even in situations like this, sometimes we use continuous model just for prediction or for some other reasons, for other purposes. Okay. So just know that in terms of mathematical model wise, it is possible to have a continuous function for this scenario. So last warm-up question. Does the graph you drew intersect horizontal axes? Or how about the vertical axis? If so, where? If not, why not? Again, take your time. We're just trying to have you think before we dive into the ideas of graph. So again, this question, the answers I'm going to show you are based on the input quantity as workers. Okay. So let's look at the answers. The graph cannot intersect vertical axis. If there are no workers, the crop will never be harvested. So 0 is not in the domain of this function. Graph also cannot intersect horizontal axis. No matter how many workers there, the amount of time it takes to harvest the field will always be positive. So in this scenario, we cannot have a negative time or 0 time to harvest. Even if it takes really split second, very small amount of time, still there's a positive time that has passed. Okay, so something to think about. So the graph represents a function. When graph represents a function, we do have to be mindful about the domain and range and relation between two quantities, input and output quantities. So starting next page, we're going to look at some toolkit function. So toolkit is just a name. We also call it basic function that we need to be familiar with in terms of shapes and its trend. So first function is called constant function. It's called constant because output is just a number, constant. Okay. So here's an example. This is f of x equals 2. That means whatever the input is, the output is always 2. And it is a function because each input has only one unique output. Right? And that output happens to be 2 for all the inputs. And this table is just a tool for us to use to point out some coordinate points. Okay, so these are not all the points are here. This is some of the points. So negative 2, 2, 0, 2, 2, 2. Okay. So this table shows, okay, let's find some points and connect them. Okay, because these functions are continuous unless we have a specific restriction. Depends on the context of the problem. Okay, so we create 3 dots and we connected it. Oops, sorry. An identity function is identity because input and output are same numeric values. So f of x equals x, also known as y equals x. So when input is negative 2, output is negative 2. When input is 0, output is also 0, 2 and 2. And this has diagonal line passing the origin. So again, this is not all the points on this graph. And actually, we cannot list all the points because there's infinite number of them. We plot few of them, then connect them. Okay. That's one way to draw it. Okay, especially in the beginning when trying to get used to these ideas. Okay, absolute value is f of x equals absolute value of x. Again, input, whatever input is, we get absolute value. So when input is -2, we get 2, 0, 0, 2, and 2. And we have this V shape. Okay, so you can think as similar to this one, but this negative output quantity become positive quantity. Now we have quadratic. Quadratic is f of x equals x squared. So whatever the input quantity is, we square the input quantity to get an output quantity. And we have this parabola shape. And here's some few points. Okay, but the important thing is quadratic, x squared. It has shape of this curve, parabola shape. That's something you need to be familiar with. And cubic is we take the third power of the input quantity and it has shape of this. And here are some examples. Okay, and let's look next page. We have reciprocal, which is 1 over x. So whatever the input is, we take the reciprocal of the input, which is 1 over x. So interesting about this function, we cannot have 0 as a domain because 1 over 0 is undefined. Therefore, we do not have a value at 0. So as x approaches 0 from the right side, as we plug values smaller, positive number close to 0, number gets bigger and bigger. So there's a trend of going positive infinity here, trend of going negative infinity here. And reciprocal square, we just square the bottom. So very similar to this one, but now bottom part, this part becomes positive here. Then we have square root f of x equals square root of x. It has shape. So this one, it starts at 0. Because again, we really have to be mindful of domain. This is the first function we saw. Well, not first, but this is one function that has restrict domain that is more than just excluding 0. So here we can include 0, but we cannot have any negative number. That's why you do not see any graph in this section of the graph. And we take the square root, that's the output. Here are some example points. And we have cubic root. Cubic root, we can have negative number, right? So that's why we have a negative side here. Okay. Oops. So those are some basic functions that we need to be familiar with, know the shape, or be able to graph them, right, by plotting some points. So let's look at the idea of even and odd function. An even function is when I plug negative x, I get f of x for all domain of f. Okay, so whatever the function is, I input negative value of that input, same input quantity, then I get same output. Then that's an even function. An odd function is I insert negative x, but then output will be negative f of x. Okay, so let's look at some examples. So using definition to decide whether each function is even, odd, or neither. So here we have function f of x equals negative 3x to the fourth plus 6x squared plus 1. So we want to see how negative f of x relates to f of x. So what we have to do is we simplify f of negative x. That means here, instead of x, I plug negative x to this, all these function terms. Then f of negative x, we'll get negative 3, negative x to the fourth plus 6 negative x to the second plus 1. And when I simplify, I get this one. And as you can see, that one right there is same as f of x. This right here is same as the given function f of x. So what happened is I just put input negative input quantity, negative x. That gives you same output as if I were to plug in just x as input quantity. Therefore, this given function f of x is an even function. So let's look at the next page for another example. Use the definitions to decide whether each, so this function, is even, odd, or neither. So same idea, we need to see how g of negative x relates to g of x. So we just plug negative x here instead. Then simplify, and we saw that this one is not same as g of x because it has negative sign. this is also not same as negative g of x. In order to be negative g of x, we have to multiply negative to all the three terms. So had this been negative x cubed minus x squared minus 1, then this wouldn't be an odd function. But since it's not negative x, this is not an odd function either. Therefore, g of x is neither even nor odd. Functions do not have to be even or odd, just like function does not have to be one-to-one function. Okay. You might be surprised that degree of g of x is odd, right? Here, this is with odd degree, but it's not an odd function. That's something to keep in mind, because this is the only way we can verify even odd functions, okay, when given an equation. So just having an odd degree does not make an odd function. That's not necessarily related. Nor the having even degree doesn't mean that we're going to have an even function. We have to verify using the definition given in previous page right here. So I'd like you to pause the video and try this one. Okay. Use the definition to decide whether this following function is even, odd, or neither, just like I did 30 seconds ago. So pause the video, submit your answer in the Canvas. This should be on module 3 variable video problem on the week 3 tab. Okay, so pause the video. Once you're done, come back to play again the video. Okay, now we're going to look at transformation of functions. So what's happening to transformation is basically we're affecting the input and output quantities. So once we change input and output quantity of functions, the graph will look different. So vertical shift, which is also known as output quantity shift. That means that for a given function, f of x, a new function, if I add a number k to a function. So again, f of x itself is already an output. So to this output, I'm adding k. So that means whatever output I got from f of x, I'm adding a number or subtracting a number. Okay. So all the output quantity changed by k units. So if k is positive, graph will shift up because all the output quantities increase same amount, or all the output quantity will shift down. So let's look at an example. So this function f of x, I add plus 1. So that means this entire graph shifts 1 unit up. So here is, we can pick some points and we can increase all by 1. But the main idea is that this graph, this blue or teal color graph, shifts up by 1. So now we transfer the vertically 1 unit. Again, think about in terms of output quantity. It's shifting up because y-axis represents output quantity. And since we're adding 1 to the output f of x, that's why entire graph goes up. If we're subtracting, it would go down. Horizontal shift. Now for horizontal shift, what we're doing is we are shifting the input quantity, then insert the input quantity to function to get an output. So here, as you can see, we subtract. Now we have to pay attention here. F of x minus h is a new input, where h is a constant, horizontal shift the function. Now if h is positive, then graph will shift right. If h is negative, then graph will shift left. So again, we have to pay attention to this form here. If h is positive, then the function will stay x minus h. For example, if h was 2, then we have f of x minus 2. If it was f of x minus 2, then it will shift right to 2. Okay. If h is negative, for example, if h was negative 3, if I plug negative 3 here, negative gives me positive, so I'll have x plus h. So if you see f of x plus h, that means the graph will shift left. So the sign is opposite, right? So keep that in mind. So here's an example graph. Here, I have f of x. Then I have what actually essentially we have here in input quantity is x minus -1. So we actually go left 1. But if I simplify, minus -1 becomes +1, right? So we do have to pay attention. It's not as simple as the vertical shift where we just add 1, go up, subtract 1, go down. Okay. You can think as a sign opposite. +1 means we go left 1. -1 means we go right 1 in terms of horizontal distance. So vertical reflections. So given a function f of x, a new function g of x, now we're multiplying -1 to the output. So that means all the positive output quantity becomes negative, and all the negative output quantities become positive. That's why it causes reflection. Okay, sometimes it's called reflection about or over through the x-axis. So let's look at an example here. Here I have this function s of t, which is known as square root of t. So for vertical reflection, I'm going to multiply -1 to this entire function. That means I'm going to multiply -1 here. So then that's what I get. So negative square root of t looks like this right here. We're reflecting over the x-axis. Okay, we're multiplying negative to entire output quantity, which is why causing us to have reflection over x-axis in terms of graph. Okay, so we're multiplying negative to entire output quantity. Now horizontal reflections is multiplying negative to input quantity, -x, and we insert that negative to the output. So here's an example. S of t is square root t. Then to new function, I'm going to, well, I should call it h, but the new function, I'm going to call it -t. I'm going to insert -t to the input. Then I get square root of -t. How does square root of -t looks like? This is the graph of square root of -t. You can think of vertical axis right here, and we reflect horizontally like this. Okay, and you can think, oh, how can we have a negative number, negative sign under the square root? This is okay. This is why it reflected. It's okay to plug -4 now, because -4 gives me +4. So -4 will give me +2 as an output. -1 will gives me negative minus or -1, which would be +1. Here's +1. So this is a horizontal reflection, which means we reflection about y-axis. Okay, so it is important for us to be able to recognize these and sketch these. Now we're going to look at vertical and stretches and compressions. So what's happening here is similar to multiplying negative number to an output. We're multiplying now a number, not just negative number, any number to entire output. Okay. So if I multiply, so A is multiplying here. If I multiply positive number greater than 1, the graph will be stretched. And you can see right here, green graph right here. So the f of x, so blue graph right here, is the, let's say the original graph. I multiply a number greater than 1, and as you can see, it will stretch. So this is different from vertical shift, the graph stretch. So you can think as you hold, you can imagine, put your finger right here and kind of stretching like a rubber band. So it's not entire graph is shifting, it's stretching like a rubber band. Okay, again, green graph still says here. Now if I multiply a number between 0 and 1, then graph will be compressed. So it goes down, like look at the red graph, it goes down. You can think as it's compressing down now. Compressed. Okay. So if you see this arrow, but vertically stretching. So actually, another good way to think about it is, I have this blue graph here. If I'm going to stretch, I'm going to stretch this way and stretch up and down vertically. If I'm going to compress, then I'm going to compress up and down. So for red graph, I'm compressing like this direction. This is an arrow, and that's kind of big arrow, compress. When a is less than 0, so negative number, then it will be combination of vertical stretch or compression with a vertical reflection. Because then if you multiply negative number first, negative number itself gives us a vertical reflection. Then we have to look at the number itself. Is it a fraction or is it a number bigger than 1? Is it a fraction between 0 and 1 or is it a number bigger than 1? Then it will be either one of these. So here we just need to understand the trend. Okay. Horizontal. Okay. As you can guess it, now we're multiplying a number to an input quantity, as you can see b of x here. Then we insert the b of x to the output to get an output. So here, if b is greater than 1, then graph will be compressed by 1 over b. Okay. So let's look at the blue again. The blue graph here is the original graph. Now I multiply 2, then insert 2x as an input. Then green graph is compressed, horizontally compressed. Okay. So horizontal compressed as in, now this one you can think as an elevator. Compress means we're closing the elevator door, like this direction. So that's why the green graph is narrower. And if I multiply a number between 0 and 1 to input quantity, okay, then it will be stretch. So we can think as opening the elevator door. So it kind of got wider, the red one got wider. And if, again, b is less than 0, we have to think about horizontal reflection. Then what is the number we're multiplying? Is it between 0 and 1 or greater than 1? So it will be a combination of transformation. Okay, so now video problem 2. Pause the video, then submit your answer to the problem below in Canvas. So consider this function, negative x cubed plus 2x. Which of the following represents the vertical shift up by 3 and horizontal shift left by 2? So what's the new function that if I apply the vertical shift of 3 to this function and horizontal shift left by 2 to this function? Okay, so think about it. A, B, C, D, select your answer and type your answer to Canvas. And once you submit that, you can come back to the video. Okay. Now let's look at piecewise functions. So referring back to definition function, the function consists of domain, range, and the rule. The rule, also known as like equation that we see a lot, between domain and range. So the rule can be expressed with more than one formula as long as each input pairs with one output quantity, exactly one output quantity. Because this is one of the main part of the function. So as long as this rule is kept, we can have hundreds of formulas representing one function. Such function is more than one formula is called piecewise function. So this is why very important for us to understand the definition of function. Because function isn't just an equation. Function is this broader idea that consists of domain and range, which is collection of input quantity and collection of output quantities, and a rule or the rule that relates those two quantities. And the rule, as long as each input quantity pairs with exactly one output quantity, that entire thing is a function. So function is not just one equation always. Okay. So a piecewise function, more than one formula. So it's formula 1 if x is in domain 1. So we also have a separate domain. Okay. So let's just look at an example of piecewise function and how to graph these. So this again, we have to keep in mind that function definition, or also we can graph one by one. So again, this entire thing is a function as long as it passes the rule of each input quantity gives one output, exactly one output. Okay, so if I plug 1 here, whatever I plug in here is less than or equal to 1, I get one number. Also here, whatever I plug between this range, I get 3. And whatever I plug greater than 2, I get that number. identity function. So when we graph piecewise function, we want to graph one by one. So you can graph in one grid, or you can graph 3 separate grids and combine them. So I'm going to do 3 separate just to demonstrate. So here we have x squared. X squared is a parabola, as we saw earlier. But then less than equal to 1. That means that right here, input is less than equal to 1. So that's why function is less than equal to 1. There's a closed circle. Then it continues the parabola shape. So this right here represents this graph. Oops. This graph, x squared less than equal to 1 is this graph right here. And this closed circle here, we have closed circle because x is less than equal to 1. So when x is 1, we have x squared, which gives us 1 squared, gives us 1 as an output. Then the parabola shape continues to the left. So then between 1 and less than equal to 2, we have 3. It's a constant function. So here 1 must be open circle because it's strictly greater than 1. So we have open circle, then closed circle at 2. And output is always 3 in this range. And closed circle again because less than equal to 2. Then lastly, when greater than 2, we have x. So x is just diagonal function. We have open circle is strictly greater than 2. So now we combine all these graphs in one grid. And this right here represents graph of this function. Again, this is a function because it passes that idea of input quantity assigned to exactly one output quantity. Right? You can also think of this vertical line test. If you have a vertical line and if you scan it to left and right, as long as the vertical line intersects with only one point at a time on the graph, it is a function. Okay. So again, pay attention here. When I plug 1 as an input, my output is 1 in this function, not 3. 3 is open circle. When I plug 2 as an input, what is output? Think about it. 3, right? 3 is the output. So 1 and 2 also gives exactly one output. 1 gives the output of 1, 2 gives output of 3. So it is a function. Now we're going to talk about interpreting graphs. So why are graphs so important? Again, sometimes the graphs are just a good way to communicate information. What information? Specifically, relations between input and output quantities. And as we can see, if function is like going up, it's increasing. So we can see that from -1 to maybe around -2 functions increasing. And -2 to +2 functions decreasing because output quantity is decreasing as input quantity increasing. And similarly, from 2 to +infinity, function is increasing. So when we say increasing, decreasing, we're generally talking about the output quantity is increasing or decreasing because we're looking at is it going up or down. And up and down means vertical, right? We're looking at vertically. But we're always assuming as input quantity increases from left to right. Okay, so that's what's happening here. So this is rather straightforward, recognizing given a graph is increasing, decreasing. But there's something more we have to pay attention to. So we're going to finish this video with this problem. So the stocks of two companies, company A and B, went up in value and both currently sell for $75. However, one is clearly better investment than the other. So this is why we really have to think about relation between two quantities, input and output. So here input quantity are time and output quantities are stock price. And as you can see, both companies' stock price are increasing over time. But one company's is clearly better investment than other. Okay, so think about it. Well, which one is better investment? And try to explain why in your mind before I go over the answer. Why is it that one company is better than the other company in terms of investment? Okay. So this is why we need to be able to explain more than just increasing, decreasing. Because there are different types of increasing and there's different types of decreasing. So let's look at the reason. Company A, as time increases, stock price increases at a decreasing rate. So what does that mean? So how do we think about this? So that means for uniform successive change in time, so let's say this amount of time and this amount of time. So let's say maybe first 3 months and second 3 months. So first 3 months, so months 1, 2, 3, and month 4, 5, 6. So uniform successive change. So we have same interval of change, let's say. So we manually construct this time interval. We divide time interval to equal parts. Then we look at how much it changed between first 3 months. It rose higher. It rose more than next 3 months, right? The amount of high change between these two is decreasing. So again, the overall function is increasing, but it is increasing at a decreasing rate because uniform successive change in time, for uniform successive change in time, the amount of stock price changes decreases. It is increasing, but amount of it increases decreases every time interval. That's why company A, we can say stock price is increases at a decreasing rate. For company B, as time increases, stock prices increases at increasing rate. So same idea, if you can construct the same time interval. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. The amount of height it changed between first 3 months is smaller than amount of change it changed between next 3 months, and even more here, right? So for uniform successive change in time, the amount of stock price change is increasing. That's why the stock price is increasing at an increasing rate. So in this case, for this scenario, company B will be a better investment. So when you look at the curve, this curve just can describe more than just relations between two quantity when we think about just x and y. In terms of context, like these problems, it can give us more information about the relation between two quantities. Okay. So it is helpful for us to understand how this curve shape is increasing at a decreasing rate or increasing at an increasing rate. Same for decreasing as well, decreasing at an increasing rate, decreasing at a decreasing rate.